Let's build a machine learning model using polynomial gradient descent algorithm and understand how it actually works.
So today we're building polynomial regression completely from scratch. We're gonna use only NumPy and basic Python, but in the end of this video I will show you how to build it with scikit-learn library just in a couple lines of code. But for learning purpose now we're gonna build it from scratch. So by the end of this video, you'll understand what polynomial regression actually is, how gradient descent works, and why we need normalization, and how to build a real machine learning algorithm from the ground up. So first, what is polynomial regression and why do we need it? Imagine you have data that looks like a curve, not a straight line. Linear regression can only fit straight lines, but what if your data follows a parabola or some other curved pattern? That's where we use polynomial regression. A linear equation looks like y equals 2x plus 3, which gives you a straight line, but a polynomial equation looks like y equals 2x squared plus 5x plus 10, which gives you a beautiful curve. The key insight here is this really important is that we can actually transform polynomial regression into linear regression by creating new features. And here's how it works. If we have x as our input, we create 3 new features. X to the power of 0, which is just 1, and we call this the bias term. X to the power of 1, which is just x itself, and x to the power of 2, which is x squared. Now our curved equation y equals 2x squared plus 5x plus 10 becomes a linear equation in 3 features. In the same equation, just represented just differently. And this transformation is the entire secret behind polynomial regression. Alright, so let's start building. First, we create our class and initialize it with all the parameters we'll need. We start with the class definition and the init method, which set up everything. And the first parameter is degree, and we set it to 3 by default. This tells us the highest power of x we'll use. If degree equals 2, we get the features 1, x and x squared. If degree equals 3, we get 1x, x squared, and x cubed. You can think on this as how curvy we want our fitted line to be. So the next is learning rate. We usually set it by 001 by default. This is super important for gradient descent. You can think of it like walking down a hill to find the lowest point. And if the learning rate is too big, like 0.5, you'll take a huge jumps and might overshoot the bottom completely. But if it's too small, like 0.0001, you'll take tiny baby steps and it'll take forever to reach the bottom. And the value like 0.01 is usually just right, giving you steady progress toward the minimum. Then we have an iteration set to 5,000. This is how many times we'll update our coefficients during training. So each iteration is one step down the hill we're trying to descend. And more iterations generally means better training, but there's a point of diminishing returns. We initialize self-coefficients to none because we don't know what they should be yet. These are the weights we are trying to learn, the A, B, and C in our equation. Y equals ax squared plus bx plus c. And we'll set this properly later during the training. So we create also self-loss history as an empty list. This will track how our error change over time during training. And it's super useful because we can plot it later to see if we are actually learning or if something going wrong. Similarly, self-value loss history tracks the validation loss. This is separate from training loss and helps us detect if we are overfitting. If training loss goes down but validation loss goes up, we know we are memorizing the training data instead of learning general patterns. And finally, we have self-train loss, self-train lost, self-train test loss, self-train R2, and self-test R2, all set to none. This will store our final performance metrics after training is complete. So we'll go back to this after. Okay, so now we go on the really cool part, transforming our single feature x into polynomial features. This is actually where the magic happens and lets us fit curves instead of just straight lines. So the method is called polynomial features, and it takes x as input. The underscore at the start is a Python convention, meaning this is a private method just for internal use. And inside, we first create an empty matrix with np zeros. The matrix has as many rows as we have samples in x, and as many columns as degree plus 1. So if degree 2, we get 3 columns. Then we loop through each power from 0 to degree. For each power I, we will fill the ith column with x raised to this power. So let me show you a concrete example to make this crystal clear. So say we have x equals 1 to 3 and degree equals 2. We create an empty 3 by 3 matrix. When I equals 0, we set the first column to x to the power of 0, which is just 1, 1, 1. And this is our bias term. When I equals 1, we set the second column to x to the power of 1, which is just 1 to 3. And this is our linear term. And when I equals 2, we set the third column to x to the power of 2, which is 1, 4, 9. So it's our quadratic term. So our final matrix looks like this. First row is 1, 1, 1, second row is 1, 2, 4, and third row is 1, 3, 9. So each row represents one sample, and each column represents a feature. This transformed matrix is what we actually use for training. So making predictions is simple thanks to matrix multiplication. The entire prediction function is just one line. Return x self-coefficients. That symbol is a Python matrix multiplication operator, also called the dot product. And let me show you exactly what it does. Say x is a matrix with one row, 1, 2, 4. And say our coefficients are 10, 5, 2. The matrix multiplication computes 1 times 10 plus 2 times 5 plus 4, 1 times 10 plus 2 times 5 plus 4 times 2, which equals 10 plus 8, which equals 28. And notice this is exactly the same as evaluating the equation y equals 10 plus 5x plus 2x squared when x equals 2. We get 10 plus 5 times 2 plus 2 times 4, which is 10 plus 8, which equals 28. So this is the same result. And the beautiful thing is this single line of code computes predictions for all samples at once. If we have 100 samples, we get 100 predictions instantly. So this is the power of vectorization using matrix separation instead of loops. And also we need a way to measure how wrong our predictions are. And that's what the loss function does. Our loss function computes the mean squared error, which is super common in regression. And the code is simple. We take y true minus y predicted to get the errors. Square them all and then take them in. Let me walk through an example with real numbers. Say our true values are 100, 200, 300, and our predictions are 110, 190, 310. The errors are 100 minus 110, which is negative 10, 200 minus 190, which is 10, and 300 minus 310, which is negative 10. Then we squared each error. Negative 10 squared is 100, 10 squared is 100, and negative 10 squared is 100. Finally, we take the mean. 100 plus 100 plus 100 divided by 3 equals 100. So our mean squared error is 100. Why do we square the errors instead of just taking absolute values? There are 3 good reasons. First, squaring makes negative errors positive, so they don't cancel out the positive errors. Second is squaring penalizes larger errors more heavily. An error of 10 becomes 100, but an error of 20 becomes 400, so big mistakes hurt your loss a lot more. And third, squaring makes the math work out nicely for calculus. So the derivative of a squared function is smooth and easy to compute, which is exactly what we need for gradient descent. And now we need to do the gradient computation, and this is the heart of gradient descent, computing how to update our coefficients to reduce the loss. So the code looks scary at first, but I promise it makes sense once we break it down. So we have the function compute gradients, which takes x, y true, y predicted. Inside we get n, which is the number of samples. Then we return 1 over n times x transpose times the difference between y predicted and y true. The gradient tells us this: if I increase a particular coefficient slightly, how much does my error change? Should I increase or decrease it? And by how much? That's what this calculation gives us. And let me explain the math intuitively. So our loss is the mean of all the squared errors. When we take the derivative of the loss with respect to our coefficients, using calculus we get 2 over n times x transpose times the difference between prediction and true values. In practice, we drop that factor of 2 because it just gets absorbed into the learning rate anyway. So we end up with our formula 1 over n times x transpose times the error. What does x transpose mean? The transpose flips rows and columns. If x is a 3 by 2 matrix, x transposed is a 2 by 3 matrix. It's like rotating the matrix 90 degrees. So let me show you a concrete example with real numbers. Say we have 2 samples and degree equals 1. Our x matrix has 2 rows. The first row is 1, 2 represented bias equals 1 and x equals 2. The second row is 1, 3 representing bias equals 1 and x equals 3. Our true y values are 5 and 7, and our predictions are 6 and 8. So the error are y predicted minus y true, which gives us 1 and 1. Now we compute x transpose times errors. X transpose is a 2 by 2 matrix with first row 1 and 1 and second row 2 and 3. When we multiply this by the error vector 1, 1, we get 1 times 1 plus 1 times 1 equals 2 in the first position, and 2 times 1 plus 3 times 1 equals 5 in the second position. So we get the vector 2, 5. Finally, we multiply by 1 over n, which is 1 over 2, giving us 1 and 1.5. This is our gradient. It tells us to decrease the bias coefficient by 1 unit, scaled by a learning rate, and decrease the x coefficient by 2.5 units, also scaled by the learning rate. Okay, I hope you understood this. Okay, so the fit method, normalization. Now we get to the main training function called fit. This is where everything comes together. Let's go through this step by step. And I mean really step by step. The first thing we do is normalization. We compute self-x mean, which is the mean of all training data, and self-x standard deviation, which is the standard deviation. Then we normalize the training data by subtracting the mean and dividing by the standard deviation. Why it's so important? Imagine x ranges from -10 to 10. Then x squared ranges from 0 to 100. And x cubed ranges from -1000 to 1000. This is a huge problem. Our features are on completely different scales. So when features have different scales, gradient descent behaves really badly, it bounces around erratically, takes forever to converge, and can even overflow and underflow numerically. The solution is standardization, also called z-score normalization. The formula is simple. X normalized equals x minus mean divided by standard deviation. And this transforms our data to have mean equal to 0 and standard deviation equal to 1. So every feature ends up on the same scale. Let me show you an example. If x is -10, -5, 0, 5, 10, the mean is 0 and the standard deviation is about 7.7. After normalization, x becomes roughly -141, -0.71, 0, 0.71, 141. Now all our features are nicely centered around 0 with similar ranges, and gradient descent can work much more efficiently. Next, we handle the validation data if it was provided. So the code checks if x val is not known, and if so, normalizes it using self x mean and self x std, which is standard deviation. And this is absolutely critical and a common mistake people make. We use the training, mean, and standard deviation for the validation data, not the validation data's own statistic. Why? Because at prediction time, when we get brand new test data, we won't know what its mean and standard deviation are. We have to use what we learned from the training data. So if you normalize validation data using its own statistics, that's called data leakage. You're picking at information you shouldn't have access to during training. So the correct way is to always use the training statistics for any normalization. So the validation and test data get normalized using self-x mean and self-x std, which came from the training data only. After normalization, we transform our data into polynomial features. We call self-polynomial features on the normalized training data and store the results in X-train poly. If we have validation data, we do the same transformation on it. And for example, if X-train norm contains the values 0, 0, 0, 5 and 1, 0 and our degree is 2, then X-train poly becomes a matrix where the first row is 1, 0, 0, 0, 0, 0, the second row is 1, 0, 0, 5, 0, 25, and the third row is 1, 0, 1, 0, 1, 0. Each sample now has 3 features instead of 1. But before we start training, we need to initialize our coefficients. We set a random seed for reproducibility, then create random coefficient using np-random and multiply by 001. Why do we need a random initialization? If we started with all zeros, all our gradients would be 0 and we'd never learn anything. The model would be stuck. We need to break symmetry with random values. And why multiply by 001 to make them small? Large initial values can cause exploding gradients, unstable training, and overshooting the minimum. So small values like 001 give us a gentle start. For example, if a degree is 2, we need 3 coefficients. After setting the random seed and generating random numbers, we might get something like 00049, 00086, and negative 00014 that are nice small random starting points. Okay, and now we jump into the gradient descent loop. That's where the actual learning happens. We create empty lists for train losses and val losses, then we loop for n iteration times. Each iteration is one step of learning. We were discussing it before. And in each iteration, we do several things in order. First, in the forward pass, where we make predictions using our current coefficient, we call self-predict on x-train poly to get y-predict. Second, we compute the loss by calling self-compute loss with y-train and y-predict. We append this loss to our train loss list so we can track it over time. Third, if we have validation data, we make prediction on it and compute the validation loss. This helps us monitor overfitting. And fourth, we compute the gradients by calling self-compute gradients. This tells us which direction to move our coefficients. Fifth, and this is the actual learning step, we update our coefficients. So we subtract the learning rate times the gradient from the current coefficients. This moves us downhill on the loss surface. If the gradient is positive, we decrease that coefficient. If the gradient is negative, we increase that coefficient. So the learning rate controls how big our steps are. Finally, every 500 iterations, we print the current loss so we can see the progress. The output shows iteration number, training loss, and validation loss if we have it. And let me trace through what happens in one complete iteration. Say we are at iteration 0. We use our randomly initialized coefficients to make predictions. These predictions are usually terrible at first, so the loss is very high, maybe something like, I don't know, like any number. So we compute gradients which tell us how to improve, and then we update coefficients by taking a small step in the direction that reduces loss. In iteration 500, we make new predictions with our updated coefficients. The loss has decreased significantly to another number, and we keep going. By iteration 1000, loss might be down again, like by iteration 2000, down again, and so on. So the loss keeps decreasing as we learn better and better coefficients. And that's the gradient descent in action, slowly walking downhill to find the minimum loss. After the training loop finishes, we save our loss history. We assign train losses to self-loss history, and we have validation losses. We save this too, otherwise we set it to none. Why save this? Because we can plot it later to visualize the learning process, and we can see if the loss is smoothly decreasing, if it's bouncing around, if it's converging in a stable value. So we can also check if training loss and validation loss diverge, which would indicate overfitting, and it's pretty useful. After all iterations are done, we compute final performance metrics. We make predictions on the full training set using self-predict. Then we compute the mean squared error between the true training labels and our predictions. And we store it in self-train loss. So we also compute the R-squared score and store it in self-train R2. If verbose is true, we print out these final metrics so the user can see how well the training went. Then we return self, which allows the method for method chaining if someone wants to do that. But let me explain what R-squared means, because it's really useful metric. R-squared tells us what percentage of the variance in Y our model explains. If R-squared equals 1, we have perfect prediction. If it's like 0.8, we explain 80% of the variance, which is pretty good. If it's 0, we're no better than just predicting the mean every time. So if it's negative, we're actually worse than predicting the mean, which means something is seriously wrong. So yeah, that's also a pretty important metric. The predict method is how we make predictions on new data after training. It takes X as input, which could be test data or any new samples we want to predict. So first we normalize X using the training mean and standard deviation. This is crucial. We use self-x mean and self-x std, not that statistic of the new data. Then we transform the normalized data into polynomial features using self-polynomial features. Finally, we call self-predict with the polynomial features to get our predictions. The three steps are normalize using training statistics, transform to polynomial features, and multiply by learned coefficients. This ensures that new data goes through exactly the same preprocessing pipeline that the training data went through. The evaluation method. The evaluate method computes multiple performance metrics on a test set. It takes X test and Y test as inputs. First, it's called self-predict to get predictions. Then it computes 4 different metrics. Mean squared error, MSE, and the average of squared errors. It penalizes large errors heavily and has units of Y squared. Root mean squared error, or RMSE, is the square root of MSE. And it has the same units as Y, which makes it more interpretable. We can say something like, on average, our prediction are off by 5 units. So mean absolute error, or MAE, is the average of absolute errors, also in the same units as Y. It's not as sensitive to outliers as MSE, so sometimes it's better to use this one or use both. So R squared is the percentage of variance explained, which is scale independent and easy to interpret. And we store MSE as self-test loss and R squared as self-test R2. Then we return all 4 metrics in the dictionary so we can access whichever we need. Okay, so then we generate some synthetic data. It's going to be quadratic data. I'm not going to explain this function, but we just need this data to train. The train test split function splits our data into training and testing sets. First, we get the total number of samples, then we create a random permutation and indices from 0 to n minus 1. This gives us a shuffled order. Then we reorder both x and y using the permutation, which randomly shuffles our data. If our data was sorted, we might end up training on only small values and testing on large values, which would give misleading results. And now we calculate the split index as 80% of total samples if test size is 0,2. And we split x into x train using the first 80% and x test using the last 20%. So we do the same for y. Then we return all 4 arrays. The experiment function is everything together. So first we print a header, then we generate our quadratic data by calling generate quadratic data. This gives us 100 samples with the true underlying quotation being 2x squared plus 5x plus 10 plus noise. And we split this into training and tested sets using train test split. Now we have 160 training samples and 40 test samples. But we are not done splitting. We further split the training data to create a validation set. So we take 80% of training data, which is 128 samples for actual training. The remaining 32 samples becomes our validation set. So our final split is 128 samples for training, 32 samples for validation, and 40 samples for testing. This is a common pattern in machine learning. Next, we create our model with degree 2, learning rate 001 and 3000 iterations, and we call fit with the training subset and validation set. The model trains for 3000 iterations, printing progress every 500 iterations, and we'll see the training loss and validation loss decreasing over time. After training completes, we evaluate on the test set by calling model evaluate. That gives us our final performance metrics, and we print our MSE, RMSE, MAE, and R squared for the test set. These numbers tell us how well our model generalizes to completely unseen data. When you run this, you'll see output like iteration 0 with training loss around I don't know, the number and so on. So the loss should keep decreasing. Okay. And we built our first model from scratch. And let's now see how we can do it with scikit-learn library, just in couple lines of code. Now let me show you how to do the exact same thing using scikit-learn pipeline. This is what you actually use in real projects because it's clean and simple. And first we generate our data the same way. We create 200 samples following our quadratic equation y equals 2x squared plus 5x plus 10 plus some noise. Then we split it 160 samples for training and 40 for testing. We further split the training data into 128 samples for actual training and 32 for validation set. We create a pipeline object. Think of pipeline as a sequence of steps that happen automatically in order. We give it 2 steps. Step 1 is polynomial feature with degree equals 2. This does exactly what our polynomial features method did. It takes x and transform it into 1xx squared. But we don't have to worry about the details, scikit-learn handles it. Step 2 is reach with alpha equals 1, 0. Reach is regularized linear regression. It's similar to what we built, but instead of using gradient descent for 3000 iterations, it uses an analytical solution. That means it solves the problem directly using matrix algebra, and it's instant, so no iteration needed. Alpha parameter adds L2 regularization, which helps prevent overfitting. It's like a penalty for having coefficients that are too large. This is something we'd have to add manually to our from scratch version. And that's it. These 2 lines create our entire model. Pipeline automatically handles the pre-processing and training in the correct order. And now we train the model. 1 line, it's model fit, and that's all. No loops, no tracking loss, no manual gradients updates, just 1 line and we are done. The pipeline automatically transforms the features using polynomial features, then trains the reach regression on those transformed features. Okay, so after training completes, we evaluate on all 3 datasets. We make predictions on training data, validation data, and test data, and we calculate R² for each. And you'll see they're all very similar. Finally, we can look at what the model learned. We access the coefficients from each step using model named steps. And we compare that to our true equation. So what's the difference between our from scratch version and this scikit-learn pipeline? Our version used gradient descent to 3000 iterations and we had to code everything manually. The scikit-learn version uses an analytical solution, completes instantly, and it's just a few lines of code. So both give you nearly identical results. Our from scratch implementation taught you how gradient descent works. So the scikit-learn pipeline shows you how to build production systems. You need both skills. Understanding the math makes you a better engineer, but knowing the tools make you productive.
So I hope it was helpful. If you want more tech content, subscribe to this channel, and all the links you can find in the description.